This is section 1.6, exponential models. I'll follow up to quadratic models. So exponential models, we will, and again, see this hockey stick shaped graph, which we'll see in a minute. I will do some graphs, but let's just get some basics down. And the first thing is what they call the exponential number, or the Euler number, which is approximately 2.718, and this continues on from there. It's very similar to pi in that it is irrational, so it doesn't repeat or terminate. So kind of the same idea. So we have this, you know, if we wanted to use a number value to plug in it for, typically we'd go out 3 places and just use 2.718 for that value. So with that in mind, let's go ahead and do some examples that would expand out the value of E. So for, as you can see in PowerPoint, we have E to the 3rd power, or it's actually E to the 2nd power, which if we do that on the calculator, it comes out to E to the 2nd power, as you can see, comes out to 7.38 when you work it out. Now it looks like the screen's a little bit clearer. Actually, we probably could go to 7.39 if we round the 2 places. Now, E to the -3, remember that's essentially 1 over E to the 3rd power. And that would be, if we did that on a calculator, it would come out to 0.05. And then if we do E to the 1/3 power, you would get 1.40. So that's just kind of how it works out if we just plug in those values into the calculator. My cat almost got in the screen, but he didn't. That would have been only appropriate with Halloween coming up, and he's a black cat, so it would have only been appropriate, but he didn't actually get in the way. All right, so what I'm going to do next is actually graph this function y equals e to the x. So what I'm going to do is we're going to graph again by picking 5 values for x, and I'm going to do a wide range from -1 to 2 using -1, -2, -1, 0, 1, and 2. And then we're going to find the corresponding values for y, which will be e to the -2, e to the -1, e to the 0, and e to the 1st, and e to the 2nd. Now, since we're graphing it, really, why don't we? I'm going to, as there was the black cat, to bring in the Halloween spirit, of course. But anyway, if we were to plug these in the calculator, e to the -2, for example, it's going to be about 0.135. And like I said, we can really only graph to 1 decimal place, and even that's kind of a stretch. So going down, I'm just going to go ahead and slide up to the next, to go to the PowerPoint slide, and you're going to see that's what you're going to get if you complete the chart. You're going to get 0.1, 0.4, 1, 2.7, and 7.4. So I'm going to sketch a graph of those. So we'll do sketch my x and y axis. And this will be -2, 1, 0, 1, and 2. And we probably should go up to about 7. because my highest value is 7.4. So if we plot these points, it's negative 2.1, negative 1.4, 0, 1, 1, 2.7, and then 2 and 7.4. 1, 2, 3, 4, 5, 6, 7. And I estimated those. I kind of did that quickly. Again, I'll recap. It's just over the negative 2 and up 0.1. You barely are going to be above the x-axis. And then negative 1 and up about 0.4, maybe half, almost halfway. 0, 1 shouldn't be an issue. 2, 1, and about 2.7 estimates about there. And then 2 and 7.4 is there. And if I sketch the curve, you can see that I get that hockey stick shaped graph that represents e to the x power. And as you can go to the next slide, you will see a computer generated graph, which looks the same. So let's talk about, and again, I got a cat on the graph. She has to make her debut today, evidently. So meet Bindi is her name. So I'm going to go to I'm going to talk about exponential growth next, which will be number 3. So the idea of exponential growth is we start out with initial value, and what happens is that will grow and then we'll predict the final value. So the model is clearly for a situation where you have an initial value, maybe it's a population, or it could even be the number of coronavirus cases since we're in this pandemic right now. And then we will use the formula to calculate the new value. We will see a growth rate. And as you can tell from the last sketch, that curve, that growth rate is going to grow rapidly. That exponential growth grows much more rapidly than the other models do. So let's look at an example. The population of the US is 320 million. What would be the population of the US? What would be the population of the US in 20 years if it would grow at a steady rate of 0.7? So our key formula is this: P equals P0 times e to the kt. Remember, k was the rate and t was the time. I'll go back to that for just a second. So that growth rate will be a percentage rate, which will be represented by the variable k. K is time. It could be seconds, days, years. It will say in the problem. So since I don't have a lot of space up here, I will write down the values here because we just don't have much space. So our initial population, P sub 0, that is just a subscript to separate it from P. That's all it is. Don't worry about using it in the calculation. So P is 320. Of course, E we just use in a formula. Our growth rate is 0.7%. So remember, when we move the decimal 2 places, that's represented by 0.007. And our time period is 20 years. So if we go 320 times e to the, and if I work this out on the calculator, it's going to be 0.14. And if we go e to the 0.14 times 320, as you can see, that's about 368 million people. Now the value for, you can do it on your calculator, the value of e to the 0.14, you can see that, oh, the lighting in here is, it's about 1.1502, and if you times that by 320, see, that's how I get 368. I kind of let that step out. Okay, so that's an example of an exponential growth model. So let's do one more. The population of Blacksburg, Virginia is 41,000. What will be the population in 10 years if Blacksburg would grow at a rate of 1.1% per year? So again, our key values, I can probably put them up here. P0 is 41,000. Our growth rate is 1.1%, or if we move the decimal, it's 0.01. And then the time period is 10 years. So this will be set up as 41,000 times E to the 0.01 times 10. So you always do the exponent part first. We got to get that simplified down so we can find E. So this will be E to the 0.1. 10 times 0.01 is this 0.1. So if we go E to the 0.1, it's going to be about 1.05. So if we go 41,000 times 1.10517, basically, we get, and I'm just going to round to the nearest whole number, you're going to get about 45,000. That's slightly different on my slides, so let me see. That is slightly different. I wonder what I did. I must have rounded. I bet you what I did. I know. Let me do that again. If I do 0.1, yeah, if I round that to a 2, let me try that. 1.1052 times 41,000. I must just have a typo there. So I'm getting, I'll fix that, 40,313. I should be able to just change it up here. Yeah, let me double check that just one more time, just to make sure it's okay. And it's a, this is kind of for the purpose of estimating. You're saying, well, what about, what's the difference between 20, 30 people? It may not make that much difference if Blacksburg is using this to figure out, okay, do we need to, improve our schools, make more, make bigger schools, or, do we have to make adjustments according to the population? Sometimes that happens. If the area grows too fast, it outgrows its infrastructure, and they have to make changes to schools and roads and all that stuff. So it is important. But just to get an estimate of what it is, I'm going to go ahead and do that one more time just to make sure that we have the right. Oh, wait a minute. I see what happened. Okay, I'm glad I double checked that. I forgot to put the last digit in there. Yeah, so that value was originally correct. It was, my bad, it is 767, and I'll fix that up here too. I just dropped the digit off on my calculator, so I'm glad I caught that mistake, but that is a good estimate of what the population should be. Okay, so I'm going to go to decay now. So exponential decay works almost the same way, with the exception K is now going to be negative. So as you can see, my formula is P times P0 times E to the negative KT. Those values are identical. We're doing initial value, new value, rate, and time. So those actually don't change. So again, I try to keep the zoom time down. I'm going to do one example of decay. So let's do, actually, I think I'll do number 7, or yeah, number 7. And it says a certain isotope decreases at a rate of 5% per year. So my value I will plug in will be 0.05, and it will be negative. But K itself is still positive, but the formula has a negative in it. So we do need to be aware of that. My initial amount is 340 grams, and my time period is 20 years. So if I set this up, it'll be P times P0 to the E to the negative K times T. So that will be 340 for P0, negative 0.05 for the rate, and 20 years for the time. So 340E, again, we work out the exponent. That's going to times 0.05 times negative 0.05 times 20 actually comes out the negative 1. And E to the negative 1 is approximately, I'll bring the solution up in the PowerPoint as well, is about, we did this early, I think it's 0.37 roughly. I want to be a little more accurate than that. It is 0.36788. I'm just going to round the fifth place up to 8. It was followed up by 9. So anyway, if we times that by 340, you get 125 grams of the isotope. So in conclusion, one more, number 8, say you have an isotope that has 150 grams and it decreases at a rate of 6% per year. What will be, how much of the isotope will you have left after 25 years? So I'll give you a minute to look at that and think about it. So what we'll do, we will set it up this way. We'll have, and again, we got our CAT contribution to the lesson today. That's what I get for doing this from home. Anyway, P0 will be 250 times E to the 0.05 times T is 25. And if we multiply those two numbers in the exponent, we get negative 1.5. And you can actually just do that on one line on your calculator. It's actually better to do it that way because then you don't have to worry about rounding error. So if you go 250 times E to the negative 1.5, you get 56 grams. And I forgot, I do have a typo here. This one really is a typo. I need to make that 1,000 equal to 340. So I'll have to add that in there again. 340. Fortunately, I gotta go. Hold on. I don't want to erase that. There we go. And I will make that larger. Maybe not that large. How about there? That works. And there's your final answer. So the final one came out to 56 grams. That concludes this lesson. So basically, be able to work a decay model and a growth model. And I kind of went over what the graph of e to the x looks like. So most exponential functions will have that same type of curve. So the next unit we will have will be on section 1.7. Thanks for tuning in. See you at the next lesson.